Okay, so today I'm going to talk, so starting in on chapter 5, I'm going to talk about covalent bonds and covalent bonding. So in chapter 4 we talked all about ionic bonding, which had to do with electrons being transferred from one element to another, or from, and two ions, polyatomic, monatomic, whatever, of opposite charges coming together to form this big lattice. Now we're going to talk about the bonding that happens in molecules. So covalent bonding is, simply put, the sharing of electrons. So where ionic bonding happens between two or more nonmetals, ionic bonding happens between a metal and a nonmetal. Covalent bonding is between two or more nonmetals. Covalent bonding is about sharing electrons, and it's important to know that unlike the lattices formed by ionic compounds, they exist as discrete molecules. Also, they may be solids, liquids, or gases, whereas ionic compounds are almost always solids. Covalent compounds are usually low melting point solids, so solids that melt easily, liquids, or gases. So, also, if a covalent substance or a molecular compound dissolves in water, the solution doesn't conduct electricity. So salt water conducts electricity. Sugar water doesn't. Okay, so let's talk about molecules. Molecules are the fundamental units of substances formed from covalent bonds. So a molecule is a discrete unit of two or more atoms bonded together to function as a single unit. And there's a physical divide between one molecule and the next, right? There is no chemical bond that holds them together. We will talk about why water sticks together, but it's important to know that in a ionic compound like salt, all of the ions are in fact bonded together as much as there's no units separated, right? They're all just bonded together by this ionic attraction. Whereas water molecules, here's one water molecule, here's another water molecule, here's another water molecule, they are separate and distinct from one another. So, molecules are always formed from two or more nonmetals, and you always form using covalent bonds. Covalent bonds is what causes things to make molecules. Water is made up of individual molecules, and it's separated from the next, and I said this already. So, here's how it happens. Imagine we have two hydrogen atoms. So each hydrogen atom has one valence electron, right? Okay, so remember, what is the guiding principle of what makes atoms do what they do, react how they react? Remember, it's the octet rule. The atoms want 8 valence electrons, or in the case of hydrogen, 2. They want to fill up their valence shell. They want to have the maximum number of valence electrons possible. Well, these two hydrogen atoms encounter each other, and one can't rip it away from the other. It's not possible for them to do that, because they both hold on equally tightly. So they say, well, fine, we can just share. So they hang out here, and the two electrons hang out between them, and then they're happy. Each one has what it considers to be 2 electrons. Right? Another example is fluorine. Fluorine has 7 valence electrons. Right? And what's going to happen is they're going to come together, and each fluorine wants a total of 8 valence electrons, and they can share. So I'm going to draw the shared electrons in a different color, actually. I think it's a good idea. Okay, so a lot of times someone will ask me, well, okay, the red ones here, they're shared. Who do they belong to? Which fluorine atom do they belong to? And, I mean, because obviously I can't count them twice. You know, this fluorine has 2, 4, 6, 8, and then you're telling me to count 2, 4, 6, 8. My analogy is this. I have 2 houses. Now, I'm a terrible artist, so give me some leeway. That's a chimney. Right? Here's another house. They're neighbors. Right? And they both have fences. So this one here, to whom does that fence belong to? And as far as an analogy for atoms goes, I say, my answer is, who cares? Their dog doesn't get out. And that's the point. The point is, it fences in the yard. It doesn't matter who it belongs to. That's not even a consideration, right? It's that these are being shared, and this fluorine has 2, 4, 6, 8 electrons around it. This fluorine has 2, 4, 6, 8 electrons around it. And it does not matter to the individual fluorine atoms that each of them are counting these two as part of their octet. So in a way, you have already seen me demonstrate Lewis structures for ionic compounds. So when we draw Lewis structures for I did ionic compounds already, but for covalent compounds, we show, of course, like with F2, I have, my nucleus and core electrons are represented by the symbols, the F symbols, fluorine symbols, and then all the dots represent the valence electrons only. Now, these two in the middle are shared. I'm writing them in red, but a common way to show that is to do it this way, is to make a line between them to show a bond. And this shows that those two are shared. Each line is two shared electrons. So that's how we do Lewis structures. And we can get much more complicated. Like, we can get very complicated structures in this way. Oops. We can get very complicated structures, and even more complicated than this. But my point is that you can follow that these are valence electrons that are not being shared, and this is 2, 4, 6, 8 being shared, 2, 4, 6, 8 around oxygen, etc., etc. So, I showed you, and I just showed you a polyatomic molecule. So, oxygen needs 2 more electrons, right? Oxygen normally looks like this. It needs 2 more, and that's where hydrogens come in. Remember, hydrogen only wants 2 electrons, so it's willing to share. Each hydrogen is willing to share with oxygen to do this, right? Nitrogen has 5 valence electrons. It needs to make 3 bonds. So you can kind of predict what an element's going to do based on how many valence electrons it needs. So nitrogen's going to tend to make 3 bonds. Oxygen's going to tend to make 2 bonds. And carbon and this is very important for carbon. Remember I said carbon doesn't really make ionic compounds. Carbon doesn't gain or lose electrons. What it does is it shares. More predictably than oxygen or nitrogen, carbon is pretty much always going to need to make, not necessarily always with hydrogen, but it's going to need to make 4 bonds. So carbon is going to need 4 bonds just about every time. Oxygen actually has a little more flexibility. Sometimes you'll see 3 bonds, and sometimes you'll see 2. And I'll talk about which of these are more flexible and which aren't. And we'll get into that. We'll get into drawing these in a little bit in a nice systematic way. For the moment, just sort of focus on understanding what the structure is telling you, and kind of understanding the electrons and where they're moving around. So when I'm drawing the structure, I mentioned this already, but just to have it written on the screen, bonding electrons are the pairs of electrons shared between atoms, right? So they are the lines, right? So when I show this, oops, I keep messing that up. So these are the lines. The lines are the bonding electrons, right? Oh, so funny. The lines are the bonding electrons, and each line represents 2 electrons, right? Non-bonding electrons are these. Now, they're also called lone pairs, and they're always going to show up in pairs. You're never going to... I'll talk later about having an individual single loose electron, but it's kind of weird. So we're going to talk about lone pairs. You can also have double and triple bonds. So sometimes single bonds aren't adequate to describe bonding in molecules. Let's take oxygen reacting with oxygen, for example. Again, each oxygen has 6 valence electrons. And so they go, okay, well, let's share. And so now if we count up how many valence electrons each oxygen has, 2, 4, 6, 7. 2, 4, 6, 7. They don't have enough. But what they can do is then they can share these two with each other and go, oh, okay, well, let's just share 4 electrons between each other. And that is what we call a double bond. Each line represents 2 electrons, so it's a total of 4 shared electrons between them. And it functions as a single bond. Not as a single bond, but as one big, yeah, it's a double bond. So it's one bond. It just has twice as many electrons involved. Nitrogen, of course, nitrogen has, oops, I have too many electrons on it. Let me redraw that. Nitrogen has 5 valence electrons. Has 5 valence electrons, so they can share once. And that's not going to be enough. They can share again, and they can share a 3rd time. So they actually get this. So they get a triple bond. Now, there's no such thing as a quadruple bond. It's important to know. So, now I'm going to wrap up talking about covalent bonds and bonding just by talking about the bonding tendencies. And I mentioned this already. You can generally predict the number of bonds that will be formed based on number of valence electrons. And I'm going to talk about which of these are like concrete rules that are never broken. And I'm going to talk about some of them that are a little more flexible. So hydrogen only ever makes one bond ever, 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 ever. So you never see hydrogen in the middle of a molecule like this. Like it's never in the middle like that. Hydrogen only wants the one bond for its 2 electrons. It can't handle more than that. Fluorine, one bond only ever. Fluorine's never going to make 2 bonds. Chlorine, bromine, iodine are usually one bond. So the reason I'm saying usually is what actually happens is there's sort of a hierarchy and a pecking order. And we're going to learn this a little later in this chapter. In a few days we'll talk about this hierarchy. Fluorine can bully one of these other elements into making more than one bond, more bonds than it wants to, right? But fluorine never gets bullied. Fluorine never gets pushed around. Oxygen. Oxygen makes 2 bonds. Occasionally it makes more or less, but it actually is pretty good at bullying some of these others around too. But so you'll see. Oxygen, that can be in the form of 2 single bonds or 1 double bond. Nitrogen tends to make 3 bonds, and that could be a single bond, 3 single bonds, or a double and a single, or a triple. I left out a triple, obviously. So you could have this, or, of course, a triple bond. Carbon can make 4, which could be 4 singles, 2 singles and a double, 2 doubles, any combination, as long as it's 4 total bonds there. The ones that are rules that you're never going to see broken in this class are hydrogen, fluorine, and carbon. The others you might see broken occasionally. You might see broken once in a while. But those 3 are guaranteed. Okay? So I'm going to leave it at that, and in the next video I'll actually talk about how to draw Lewis structures in a nice systematic way.